Fast am I. Good evening, ladies and gentlemen. It's very nice to see you all here this evening at this event by the Manx Geological Survey. And it promises to be a very interesting and informative evening. So this evening I'd like to tell you a little bit about this evening and introduce our speaker for this evening. So it's going to be about exploring and understanding the past climates of our island. It is, however, not on the usual modern day timescales. We often hear about the last 30 years, 100 years, the pre-industrial times, or even 200 to 2,000 years ago. No, it's not that. It's going to be on a proper geological time frame. So in fact, it's going to be a presentation on 500 million years of climate change on the Isle of Man. There we go, just as advertised. This evening's talk will be given by Dr. David Quirk. I'd like to tell you a little bit about Dave's extensive background. He qualified from the University of Liverpool in 1984 with a BSc Honours in Geology, followed by a PhD in Geoscience in 1987 from the University of Leicester. Dave has worked as a senior lecturer and MSc course leader at Oxford Brookes University, as well as being involved with various companies over the years on projects in the North Sea and Europe as a geophysicist, a principal geoscientist, a team lead, then a senior consultant to the North Sea Transition Authority, and currently as an advisor at the Technical University of Denmark. He has published dozens of scientific papers, an amazing amount of papers, Dave. And closer to home, he has worked with local colleagues to provide geological information about our island, including the publication of the geology of the Isle of Man. So I'm sure you all agree that Dave is a very well qualified scientist to talk to us this evening on this topic. So ladies and gentlemen, please give a warm welcome to Dr. David Quirk.
Thank you, Adrian Khan. Of course, he knows more about weather than the rest of us put together. But I also feel some of you may be here on false pretenses because it was advertised there was going to be a film. There may be a short video or two, but there isn't a film. Unfortunately, you're going to have to listen to me for some of it at least. So apologies for that, those that want to leave now, but yeah, I can see Charles going up. So it won't just be climate, we'll be talking a little bit about plate tectonics, which many of you'll know about. It's basically is the way of getting rid of heat from the Earth. It's a convection system underneath the crust that moves the plates, and we will actually start with a little video showing how the plates moved over time. But there won't be an exam on this at the end. You'll be glad to know. I also want to say thank you to my colleagues at the Manx Geological Survey. Dave Burnett's over there, who did a lot of the mapping. We'll be talking to a lot of the basic work. He's a PhD as well. Geologists get PhDs because they can't get jobs. That's basically that's why we're called doctors. And Charles Gard as well. You'll hear his voice during this for a short time. We'll save you having to listen too long to Charles. And Scott Pearce, I don't think is here, but he's the other member of the Manx Geological Survey. So this is a picture of the plates, the Earth's plates, about 485 million years ago. And you can see we have a small part there which is Niarbol and Peel, and most of the island is down here. Now of course the plates didn't look like the current shapes of the British Isles, but we've put them on there. This plate tectonic model I made because I was working on the South Atlantic at the time, but plate tectonic models have many people working on it. I mostly used other people's work, and did a little bit myself in the South Atlantic. But we realised after doing it, we could do this, you know, it's actually a good story for the Isle of Man as well. So at one stage I'll stop it in the South Atlantic and you'll be able to see what the idea of that work was. So we'll move it now and we'll watch, this is very, very fast, 500 million years of what happened to the plates with all this convection underneath. Look at that giant continent, and it's all going to break up again in a minute. You know, Africa and South America are now moving away, and the whole of the Atlantic has formed. Now, that's way too fast. So we'll show some images from this, and you can still see the red dots, the Isle of Man up there. And those of you that were watching, it was originally 2 dots, and they've come together and formed 1 dot. So the Isle of Man was originally 2 separate parts of 2 separate continents, North America and Europe. So the idea was to talk a little bit about climate change. There's a lot of evidence for climate in the rocks, including the Isle of Man. The way this is done, calculating past temperatures, is based on oxygen isotopes plus some other chemical geochemistry, partitioning of different like calcium and magnesium. You can work out what the temperature of the Earth was, plus or minus a few degrees. But this graph now goes from, again, the 500 million years to today. And you may recognise some of these geological names like time periods: Cambrian, Ordovician, Silurian, Devonian, Carboniferous, Permian, Triassic, Jurassic, Cretaceous, and what we used to call the Tertiary, and I'll continue to call it the Tertiary. Now, what you see is the temperature's been going up and down, and look, this is going from more than 30 degrees centigrade down to 10 degrees. This is the average for the Earth. So, of course, wherever you are, it'll be a different temperature, and it's an average over the year as well. Currently, we're about 15.5 degrees centigrade there. And you'll see that we're in a blue period. So what you've seen is the temperature's come down, it's gone up, it's come down, it's hovered in low, you know, round about this 10 to 17 degrees centigrade range, and then it gets hot again and then back down again, on average. Of course, as I say, different temperatures, different places. So it sort of shows currently we're in an unusual period of actual coldness. Now, what blue means is times of polar ice cap. So it's quite unusual in Earth's history to have ice at the north and south pole. It's normally ice-free, so it's because it's warmer. And we'll talk about the cause of this. But I'll give the hint at the moment, is it's related to carbon dioxide. And if we didn't have carbon dioxide in the atmosphere, the temperature of the planet would be around about minus 18 degrees centigrade. So it's important we have what's called a greenhouse gas, and several of them that actually trap some heat. They're trapping heat as the solar energy comes in, and then as it's reflected back as infrared radiation, that is partly trapped by greenhouse gases. It's like closing the glass on a greenhouse. And so that's important for life. Minus 18 would be tough for us. But the other thing worth noting is, you know, there's a significant range, more than 20 degrees centigrade change in difference in temperature. Also, a huge difference in sea level, plus or minus, well, it can be 70 metres higher than it currently is. Those are periods when there's no ice at the North or South Pole. Oh yes, I should mention this. We have lots of animations at this is not the Manx Geological Survey. We've got, so I've got, with my other hat on, we've got something called the Energy Sustainability Centre. Lots of animations about climate change, more emphasis on current day than past. But so, moving swiftly on. The first rocks, the oldest rocks. Most of the Isle of Man is formed of, as we know it, Manx slate. This is the chasms. probably one of Charles's drone footages. And we know the ages through radioactive dating, partly, but in the case of the Isle of Man, it's these tiny, tiny little fossils. They're called acritarchs. They're sort of marine pollen. And basically, most of the Isle of Man is composed of sediment, we now know it as the Manx slate, but that's sandstone and mudstone that was deposited in the Southern Ocean, not so far from Antarctica present day. So it was pretty cold water. It was several hundred meters deep, and on the front here of the lectern, there's some of these rocks we've cut and polished, because it sort of looks a bit boring in a wall, but when you look at it in detail, it's composed of what can be pure mudstone, dark grey to black, or pure sandstone, which can be white, which is the case in the chasms here. And it polishes up really nice, actually. Now, what I've also added here, and some of you may have said I've just put it on the slides here, because this used to be 2 slides. These fossils here, you can see that's actually a creature, not a fossil, but that's the fossil, are actually younger rocks. This is on Peel Hill in the quarry, and also another thing called a graptolite, which it looks like a tuning fork or an umbrella. Or these are also sea creatures, but they're 50 million years younger. And this was a discovery we made on the Isle of Man. There's quite a good story that made the Isle of Man famous for a while, amongst geologists anyway. So this was the situation 480 million years ago. Here is most of the Isle of Man down here. This is the British Isles, but that would be where the Isle of Man was, at the northern edge of a southern continent, a really big one, sort of occupying where Antarctica is now. And then there was an ocean. Sorry, ocean in this case is white. It's hard to colour these up. And then up here, there's a part of the Isle of Man which lies between Peel and between Niarbel and Peel, which has these younger rocks, the 430 million year age rocks. But at this stage, there was nothing here, but there were sediments being deposited here out in deep cold water. And that's part of the Iaptus Ocean story. If we move 10 million years forward, the Manx slate sediments are still being deposited. You can see one of these continents has come a bit closer. Still, this ocean was the size of the Pacific, because we're looking at the whole of the Earth here. So it was a really big ocean. And then, as we get into the Silurian, so what we were just looking at, let me go back, was the Ordovician. We go another 45 million years and we get into the Silurian, and again I'll go back, you'll see this continent here has moved northwards and is now here, and this is just the time when the sediments between Niarbel and Peel were being deposited again in an ocean, but the ocean now is really narrow, so Iapetus has shrunk up to nothing. And soon, those of you who are thinking a little bit further, there's going to be a horrible crashing sound as these continents hit each other. It's just about to happen now, and that's where it happened, or it's a zone. But you can actually put your finger here at Niarbel on what were sediments deposited on the North American continent, and sediments that were deposited on, I'm calling it ancient Europe here, this southern continent. And there is a fault line that runs between here, that runs along here. We used to get people to put carrots on this so you could dot the line, with an orange line. But that's the junction between 2 plates, and that was the discovery we made on the Isle of Man. This is what made us briefly famous at Niarbel. And so just again the ages, 430 million years, last Friday 480 to 70 million years. And I should say the Manx Geological Survey is 24 years old, so we're a bit younger than You can see it on all sorts of data, but we hadn't realised it was there until we started doing the field work. And this is a magnetic image of the Irish Sea. You might just about be able to see the coast of the Isle of Man here. This is done by measuring magnetism from a plane. And the different colours reflect different types of magnetism pointing in different ways. The rocks have this, what's called a remnant magnetism. And therefore we can use all these different types of data, which is called geophysical data, to work out where the plate boundary that we saw in the Arbel, where it goes into beyond and onto the Irish Sea. Mostly it's buried. This is unusual that you can see this. Now, when those two plates came together, it was a mountain belt, the same as India crashing into Asia. This is actually the Himalayas, not the Isle of Man, 395 million years ago, but it's the same thing, same idea. As soon as the plates stopped moving against each other, so as soon as ancient Europe stopped pushing against North America, mountain belts tend to subside. Their own weight, but also there's a large amount of plate over some hot rock underneath, and it tends to be, as soon as you have the mountain belt, it wants to pull itself apart again. And this was the case here in the Caledonian Mountains, as they're known. Of course, Scotland, it stretches on into Scotland. Scotland and Norway and parts of Northern America had this mountain belt, still has, but it's very ancient. So this is just at the end of the mountain building event. It's now into the early Devonian. As I say, now the sort of pushing of the two continents has stopped, and so the whole mountain belt is beginning to collapse or subside. And things called intramontane basins, that means between the mountains, started to develop, and you'll see those nowadays in Nevada and Arizona. And they're hot there in the US, and it was hot in the Isle of Man at this time as well. And it's reflected in the Peel sandstone, but not only was it at an equatorial or within a latitude which was hot, the Earth itself was really hot at this time, and we couldn't live in this was hot, but it's soon about to drop off into an ice age, and so the question is why, and we've got some evidence on the Isle of Man why. So now just showing a little bit more. I don't know why I repeated it, but yes, it's about to collapse as mountain belt. And this is what it would have looked like at the time. Between mountains, you'd have had a desert. And this is the Peel sandstone. Charles lives on top of it. Charles Corn there in the audience. And you can see these red rocks. They're red because they were deposited in a very hot, arid environment, or fairly arid. But of course they are dipping now. You see the beds are sloped. So originally when they were deposited they were like that. And they were deposited one on top of each other. And the reason you can keep on stacking it up is because the whole thing is subsiding. There's more and more room as the belt subsides. So there's the Peel sandstone, evidence for desert. But there's also evidence for life in there. I always tell this story, the guy who did all the work on the Peel sandstone failed to see this, so we used to make fun of him. But it's sort of hard to see, but that's a burrow. That was probably made by a crab-like creature, an arthropod of some sort, in the riverbed. So this is actually this is land at the time, but the deposits are mostly made by rivers. As you know, there was probably some wind, sand, but most of it actually came from rivers, so much more like Nevada, in fact. Now the other great thing, if you go round to the stack, is, can anybody see these vertical things here? And there's a pencil there to give you a bit of scale, but I'll put the drawing on. These are, they're not quite fossils, but they're traces of roots. these are some of the earliest land plants in the world. This is just when trees are starting to form globally, and you can see them actually in the stack. They have something around them called calcite. It's calcrete. You get that nowadays in parts of the Caribbean, but it's a hard soil. It would be hard to grow potatoes in there, but there weren't any potatoes at the time. So then back to this. So just when the peel sandstone starts to show evidence of plants, then the temperature dives away. 20 degrees centigrade or more. That is a serious change in temperature. And at the same time, and this is an interesting thing, is if you look at carbon isotopes, you can get an idea of what carbon dioxide concentrations have been over geological time. Now that black line fits with these numbers here, which are carbon dioxide parts per million. And here you've got 5,000 parts per million carbon dioxide, and here you have less than 1,000. Currently we're about 435. So we're in a time of low carbon dioxide, but there is a correlation between the high temperatures and the high concentrations of carbon dioxide. And here, at the peel sandstone, you see it was all hot, 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 bump, it went away. Now, the explanation of that, almost certainly, I would say certainly actually, based on the isotopes, is because plants started to grow on land, and they started to absorb carbon dioxide. So that first ice age we got, the first main set of ice ages, there's one strange one here, but the first main set of ice ages was related to plants, taking so much carbon dioxide out of the atmosphere that it started to get colder and colder. There wasn't enough greenhouse gases for 32 degrees centigrade average, that it was getting much closer to 10. And this is when there was ice caps. And it's strange, on the Isle of Man, there's no evidence of ice caps, there's evidence of tropical seas, because the Isle of Man was really on the equator at this stage. So although it was cold globally, it was hot actually in the Isle of Man at the time. And this is something to bear in mind, even if temperatures are changing globally, local climate and local position on the Earth makes a bigger difference. So, there we are. So that carbon dioxide, now then there's a bit of a change here. We'll talk about that later. It goes back up again. But at this period, which is the Carboniferous, there's a lot of ice at the poles. So this is the early Carboniferous. And there's the Isle of Man again. There's a pretty big continent, and actually this continent is going to crash in and form a new mountain belt beyond us. We don't need to worry about it, but you're going to end up with one really big continent soon enough. But the Isle of Man at the time was like this. Wouldn't that be lovely? There were trees, and but different trees, of course. But this is the early Carboniferous. There were plenty of sea creatures. All the sediments are submarine, but a lot of them are shallow water. You see evidence for strange reefs. This is one here. This is the same sort of reef you get. They're called stromatolites present day, but these were different ones. This lump here is a type of stromatolite, and limestone was being formed everywhere. You see this is lime sand. We had lime sand in the Isle of Man 330 million years ago, made from shells. And you can see all the shells. It's the fossils, you know, from the Lime Quarry and down on the shore in Castletown. Strange things called crinoids. Well, they're not that strange maybe. They're brittle stars and the modern equivalent of them. There are corals. And Dave knows a lot about the fossils here. But it was a tropical environment, rather nice to go snorkeling in. And in addition, there were some fish around, some really strange ones. This isn't the fish. This is a fossil that was found in a basement in Castletown, almost certainly from the Isle of Man. It's with the rest of the limestone. It's stone slabs, probably the black marble quarry. And this is a whole set of bones and bone plates that came from a fish something like this. And because we're in the Isle of Man, we call it a long-tailed fish, but it's got another name beginning with R that's 3 letters long. And it probably looked something like this, which is from Brazil. But anyway, again, we got briefly in the headlines, the Isle of Man for this one. And then, at the same time, the Manx is still subsiding. Now, what we've said was the shallow water, sea, tropical sea, the Manx have mostly subsided below the sea. They're not quite, but they're half the Isle of Man is above sea, half of it's below sea. Of course, down here it was below sea because we've got limestone down there at the time. But at the same time, as it's all subsiding down, there were fractures in the rocks that started to open. So you can imagine if something's sagging, if anything sags, you can sometimes get cracks and they start to open. Now, as this started to open, hot water came through these cracks, and these are the mineral veins. And here's Laxey, here's Foxtail, of course. This is again because of the subsidence of the mountain belt. In fact, it's starting to break open. They're starting to form a rift, like East Africa. And just to remind you what these mineral veins look like, this is the Laxey one here. It goes to unbelievable, more than 500 metres below sea level. Can you imagine digging that out? Of course, they used some explosive, but it was mostly by hand. That's higher than the Snaefell is. Incredible. And that was what was excavated for lead and zinc. Most of the mineral vein, which was a few metres wide, would be quartz, but there was also galena, which is lead sulfide, and there was sphalerite, which is zinc sulfide, and maybe a little bit of copper here and there. But that's what they were after. Incredible enterprises. You wouldn't do it nowadays. Open cast is the way, but these mineral veins were valuable when you had cheap labour. Now, not only do we have hot fluids in the subsurface, we also see evidence for volcanism. And this is Iceland, but this was, again, the Isle of Man. 329 million years ago, there was a volcanic island here, which you can see at Scarlet. And it built itself up. This is one of the main vents at Scarlet. And there's these things as well, which probably one of the best I've ever seen as a geologist. They're called pillow lavas. You can see they've got pillow shapes. There's a hammer. The hammer's about that size, 1/2 metre. And all these lumps of basalt. So this was a basaltic volcano. There's lots of basalt up here as well. But these are showing that it was deposited in water. And these are modern day pillow lavas near Hawaii, and they form by lava coming into the sea, moving along, and it's molten inside, but it cools off very quickly and forms this pillow shape. And so you can see these in submarines if you dare go near it, but we have them on the Isle of Man. And then I said that continent would get big. There it is. All the plates of the Earth are together now. Now this is a really unstable situation because you can't get rid of the heat that's underneath very easily. It's sort of acting like a blanket. So it's about to break apart again during the Permian, which we won't spend too much time on, but this time is when coal was deposited. There's lots of swamps around all in northern Europe here. It's the parts that are still above sea level are now getting swampy. And the carbon part of it is because it was coal, carboniferous. And this could be seen as the start of our problems, because we started burning coal, of course. So again, it's sort of strange. This was a time when there was ice on the Earth, but there was a lot of hots. In this case, the coal was deposited in the hot region again. It was hot and swampy. Near the equator. Now, the relevance to the Isle of Man, we don't use coal anymore, but we do still use gas. And all the gas we use in Northern Europe comes from the Carboniferous, from the coal seams. So it's still important to us, the coal, but in a different way. Now, I'll just actually go back here. That was to remind me to say, if you have ice ages going backwards and forwards, we're currently, as I say, about this temperature. If the temperature increases and the ice melts, so you just start to reach the orange point here, what would the Isle of Man look like? Okay, I'm going to take present day Isle of Man, but nonetheless, it's interesting to look at that. If all the ice was gone, we would have a sea level rise of about 70 metres. And so we would have 2 islands and there's some little ones around about as well. If Greenland ice, current Greenland ice, melts, then it would be a 7 metre rise. So it's not desperate, maybe, until the storms come along, and then it is a bit desperate. But yeah, it's interesting to see we have 2 islands and no northern plain when the sea level is high. Right, the other thing that's interesting is you may have heard of mass extinction events. We know the one at the end of the Cretaceous, but we'll talk about 3 at the start, earlier. This one here, when the Peel sandstone was deposited, was a time also of a big extinction. And again, you know, think, well, there's plants growing, surely that's good. Well, again, it was a temperature change. So most of the existing creatures, there were strange-looking creatures even on land at this stage, not many, but certainly the marine animals all died out, basically, at this time, when the temperature changed. Again, tied in with carbon dioxide. There's one, this is the Permian, this is the rifting again. You see the temperature goes up, and there's another extinction because the animals and the plants that like the cold, they die out. So every time there's a big temperature change, there tends to be an extinction event, and that's maybe 90% of the world's animals and plants. There's a couple more which are not fully explained. Oh, sorry. Or this one is a more difficult one to explain, the Triassic at the end of Triassic. This one's easy to explain. It's not due to carbon dioxide, as many of you know, but that's when the dinosaurs ended their lives. So we'll come back to that one. So far, we've talked about the geology of the Isle of Man. We've talked about the main part, which is the slate, the Manx slate. There's some granite in there, which was formed when the mountain belt was developing. We've got the Peel sand. Oh, we've got, of course, between Nearble and Peel, this younger North American piece of the rocks. We've got the Peel sandstone, and we've got the limestone, and the volcanics at Scarlet. And then we've got these sediments up here, which were deposited in the Ice Age, which is only a mere few tens of thousands of years ago. So there's the Ice Age right up here at the end of the clock. So what happened in between? We've got missing on the Isle of Man, we don't have the Permian, we don't have the Triassic, and we don't have the Jurassic, but they're off in the Irish Sea. So those of us who have a bad past that used to work in oil and gas, we used to map these rocks because there's lots of gas in the Triassic. There's not a lot of Jurassic, but there is there, and there's Cretaceous as well on the Antrim coast in Northern Ireland. Now, all of those have been removed from the Isle of Man. The whole area, the whole of the Irish Sea has come up about 2 kilometres, believe it or not. And so the only remains of these rocks which were around are out in the Irish Sea, which didn't come up quite as far as the Isle of Man. So Devonian, this is the time when we had some trees. Then, we had the mountain belt here. It starts to subside below the sea. This is I'm trying to show this over time. And all the remaining rocks, the Jurassic and Cretaceous, were removed, eroded. So the closest we get to Jurassic on the Isle of Man is a stamp. This is when most of the world's the source rock for oil is mostly Jurassic and Cretaceous. So this is the other culprit for our problems nowadays. A lot of the oil and gas comes from what's missing actually in the Irish Sea, funnily enough, the source rocks for oil and gas. And then, of course, the nearest we got to the Cretaceous is the T-Rex race. But they were here at one stage. So this is the early Cretaceous, and this is why I was working on this plate tectonic model, because we were looking down here, again, it's in my dirty past, I was looking at the rocks here in Brazil and across in Angola, and there was evidence we had this little narrow sea at the time, which was the start of the South Atlantic. The North Atlantic had already been formed. It's not big, but it's enlarging. Now, anybody? Well, let's move on a little bit further. So there we are. There's the South Atlantic has started to open. Africa is separating from South America. Now, 65 million years ago, something bad's about to happen. So the Tyrannosaurus Rex is about to lose its life because bang. If you didn't know where the Yucatan Peninsula was, it's there. It's up in Mexico. I've worked on the seismic data there. It's unbelievable what happened to the Earth there. But it affected, of course, the whole of the Earth. Probably there were clouds over everything, so it went dark. But most, no dinosaurs left. A lot of life was wiped out at that time. This is certainly a major event in the Earth's history, but it wasn't related to carbon dioxide. This one, there would be a change in carbon dioxide, but that wasn't the cause. It was the actual meteorite itself. Now, 60 million years ago, actually probably very, very close to this meteorite impact time, maybe just a few million years later, the North Atlantic was really starting to open well, and something strange happened in the Isle of Man. These we call dolerite dikes. Again, it says tertiary, it would be Paleogene nowadays, but what they are is basalt rock that's in a vertical sheet. This one's only about 1.5 meters, 2 meters wide. This is down in Pulvash. You can see it goes along here across. They're all over the place in the Isle of Man. They're not always easy to spot, but we can see them on magnetic data, which are these lines running. So there's the Isle of Man again. And these they run down from Northern Ireland. There's a whole pile of them in Northern Ireland. And they're a mere 25 kilometres deep, or deeper. These go right down to below the crust. They're incredible features, and they were fractures that filled with magma, came straight up, and run their way through the Isle of Man. They're narrow, but they have a big magnetic effect because they're full of iron and magnesium and manganese. No, magnesium. So, actually, let me go back. This is when you're going to hear Charles Gard, if I manage to click the right thing. We thought this was so interesting we made a film. This is part of a bigger film on the Manx Geological Survey, but it's sort of simple, but it gives the effect.
One final upheaval shook the region some 60 million years ago, when North America rifted apart from Europe, forming the North Atlantic Ocean. In the Irish Sea area, the crust was split apart by deep fissures that trapped magma from the molten interior of the Earth. Evidence of these magma-filled fissures can be seen as dikes on the island today.
Thank you, Charles. So you can see these here. There's one that gets up to 12 metres up at Port Corneille, but it's hard to see. These are easier to see down at Pulvash. But a major event. There were volcanoes. These fed volcanoes in certain parts of Northern Ireland. 20 million years, I thought I'd just put this in because we're always interested in our Viking neighbours up here in Iceland. Iceland is just starting to form at this stage. And you can see, go a bit further, now we've got the volcanic islands right on the mid-oceanic ridge. This is where the plates are separating, where there's volcanism, volcanic rocks. This is the Azores down here. It's still hot as well. Good place for geothermal energy. And then, so we've talked about the hard rocks. And then we've got these up here, the Ice Age sands, which are eroding for a reason, because they don't really belong there and they're not hard like the rest of the island. So that's what it looked like 20,000 years ago, and what it will probably look like 20,000 years from now as well, depending on sea level. These are the sands. This is up at the Bride Hills, of course. Lots and lots of sand that came out from a glacier that was coming down from the north, so from the Solway Firth. So I've just nipped over to Iceland here to show you what it would have looked like. And of course we've got the giant deer. Not a very good image, I must get a better one. But that would be walking around at the time. Not a lot of trees, couldn't get through with its antlers, but the trees are soon about to arrive. You know, it was fairly forested soon after this. So that's the end of the Ice Age. Now, we're looking at a different time scale now. This is 20,000 years to present day, 20,000 to naught. And here's the temperatures. Now we're not talking about 30 degrees, we're talking something from a little above 10 degrees to present day 15 and a half. And again, there's a graph over time. This is the proper Ice Age in the green here. The temperature's rising, and then we're out of the Ice Age. So that means there's still polar ice caps, but it's not, here is not icy. And this change in temperature is probably not carbon dioxide. This is probably related to cycles of the sun. They're called Milankovitch cycles. And these, there's more solar activity, less solar activity. This would probably be a time of less solar activity. This was a time of more solar activity. So 15,000 years ago, we will have the Laxi Valley looking like this. Present day, the reason it's U-shaped is because there was glacier going down it. So these variations, as I say, is called Milankovitch cycles. They're oscillations of solar energy. That varies over time, but not on the scale we've been talking about geologically in the, you know, you can't, from a solar cycle, can you get much above about 15 degrees centigrade, or couldn't to date anyway. Now, the little wobbles are actually volcanic eruptions. You can see things, but they only seem to last for about a few, you know, maximum maybe 3, 4, 5 years, and then it's back to normal again. And the reason they affect the climate is two reasons. One is the cloud, or it can go dark, but also there is a carbon dioxide and other gases effect, but it doesn't last long, unless it's a really, really big event. But currently, we haven't had a really, really big event for some time. Now, unfortunately, the Vikings chose to go to Greenland just as it started to get cold, and there's a reason there's no Vikings left in Greenland, because they chose the wrong time to move there. It got too cold. But if they went there now, it's warming, and it would be a nice time to be in Greenland if you didn't care about everything else that's going on. So why did the temperature start going up? This is right at the end of the thing, is because of industrialisation. We started burning coal, then we started burning oil, and then we started burning gas. And the temperature is rising very quickly, over a very short period, and it's going much quicker than it's ever happened geologically. So that's the future projections. This just shows what's happening in terms of, we're not quite double our carbon dioxide, but we're getting there. And if we burn all the oil and gas we've got in reserves at the moment, we'll get to a 3.2 degrees centigrade rise, which will be pretty uncomfortable in large parts of the world, and certainly will mean significant sea level rises. So that's the story. You know, say if you want to find some, it's always good to find something to blame. Coal wasn't good. The oil and gas from the Jurassic and Cretaceous wasn't good, except it did make humanity get rather quickly into the comfortable life we have now. So it's just that we might need to think about changing a little bit in the future. But it's all recorded in the Isle of Man, and so the island has been through some rough times. It was a cold seabed in Antarctica, or that sort of latitude 500 million years ago. It was moving northward due to plate tectonics. Then we got a mountain belt. We're part of the Caledonian mountain belt. And then we saw deserts, the Peel sandstone, tropical conditions, marine conditions again in the Carboniferous, the Castletown limestone, and more recently the Ice Age. And then it really was shaken and abused with volcanoes and earthquakes, so the faults and fractures would be the mineral veins and the tertiary dikes. It's been uplifted. I say this area here, over the last few tens of millions of years, come up 2 kilometres. That is a major event, and then we'll get covered again. It's just and so we see the whole story of life, the Earth's climates, and with and without polar ice caps. And the question is, what's going to happen in the future? Because I said we might get you here or we've got you here under false pretenses, and there is some time for questions. I'll just show you this one little film because I think it's sort of interesting. And we were trying to guess what would happen in the future on the Isle of Man. So let me just see whether maybe one more click. Maybe. Okay. No voice this time. So why we warm in the Isle of Man is because of the Gulf Stream. And that's a global circulation. But as the ice in Greenland melts, it will be slowing the Gulf Stream down. And 2 reasons. One, it's cold and because it's fresher than the current seawater is. So when that will happen, if we continue to melt the ice, is the question. And these things can happen suddenly. Adrian thinks it will be in 100 years' time. I think it could be sooner than that, and we thought we could make a Christmas card out of this. But it's what Norway, for instance, would also be, really cold, because we're at the latitude of northern Canada, just the southern part of Alaska. So we're warmer than we should be. So it's strange to think that climate change, global warming, might actually mean we get colder. But anyway, this is on the Energy and Sustainability Centre. A lot of we've got other material on the Manx Geological Survey website, and time for questions.